Alright folks, today we're going to talk about the multiplication counting principle and independent events. Okay, so make sure you have out your green note card. Has some of these properties that we're going to talk about today. First one up is the multiplication counting principle. Okay, so multiplication is what we're working with this time versus last time we were working with addition. Okay, so let's see the difference here. It says A and B are finite sets or countable sets. The number of ways to choose one element from A and then one element from B is found by taking the number of choices in set A times the number of choices in set B. Okay? The key here to know its multiplication is just to focus on this word and. Okay, we want to choose one from the first set and one from the second set. Okay, so that's how we know to use multiplication. That word and will help us figure out. Okay, so let's go ahead and take a look at this first option. We've got 6 drink choices, 2 entree choices, 3 vegetable options, and 3 fruit options that customers in a cafeteria may choose. We want to know in how many ways can a customer select one item from each of the groups. Okay, recall from last time this N stands for just the number of options in the group, versus if you see a capital P, that's the probability of the set or the group or the event happening. Okay, so here we want to just find out the total number of ways. Now, in our particular principle up here, we had 2 specific sets here, A and B, but this actually applies to any number as long as we're just choosing one item from each. Okay, so this can be continued. If we had a third group, we could say times the number of options for group C times options that we have continued forever. Okay, so here we're looking at 4 different options. We've got drinks, entrees, vegetables, and fruit. So we want to know just the number of choices for each of those different sets. So for part A, we've got 6 drink choices, so 6 different options for us. And we want to choose one from the entree. We only got 2 choices there, so times 2. And vegetable options, so 3 there, and choosing one from the fruit options, 3 again. Okay, we're going to multiply those all together and get our total number, 108 different ways that a customer can select one from each of those groups. Okay, on the second one, we've got Emily, who has 5 pairs of pants, 10 tops, and 4 pairs of shoes. We want to know in how many ways she can make an outfit. Again, we're talking about the number of ways. Okay, so we just have to look at the choices for each group. The first group we're choosing one from has 5 options. The second group has 10. And that last set has 4. Okay, so we're taking 5 times 10 times 4 for a total of 200 different ways that she can make an outfit. Okay, so what we're going to do next is look at a theorem that has selection with replacement, or strings with replacement here. Okay, string is just referring to your list of outcomes here. So we have S being a set within elements. Okay, if we are dealing with selection with replacement, so we're going to choose something but then place that choice back in before choosing another one, then there's going to be n to the k possible strings of length k with elements from S. Okay, so that's really confusing the way it's written right now. Okay, so we're going to actually look at an example to make sense of what that theorem is actually saying. Okay, so looking at number 3, it says how many ways are there of answering a test having 4 true-false questions? Okay, so we're just going to focus on this first part for right now. Okay, so how many ways? Well, right now, we want to see how many ways there are of answering. Okay? In order to do that, we have to know the number of choices for each group, just like we did above. Okay? What's different is all of our groups are true-false questions. Okay? So we've got two different choices here, and 4 total questions. Okay? So let's suppose we just put little blanks here to represent our 4 different questions. Okay, I know it's multiplication because I want to do the first question and the second question and the third and the fourth. Okay, well the first question is true-false, so it has 2 choices. Second one, true-false. Third one, true-false. And the last one, of course, true-false. So there's 2 choices for each of these. Okay, it's different than the previous problems because the number of choices did not change. Okay? So we're taking 2 times 2 times 2 times 2, which is 16. Okay, so there's 16 ways to answer this test with 4 questions. Okay, but let's go ahead and talk about this in terms of what we've got going on here. Okay, it says there's n to the k possible strings, or 16 possible strings. Okay, so what we did here, another way of writing 2 times 2 times 2 times 2, well, of course, is 2 to the 4th power. Okay? So what we're doing here is really having the number of choices to the power of how many times we're choosing it. Okay, so let's go ahead and fill up in our box here a little bit more clear way of writing what you got going on here. Okay, so it's definitely n to the k possible strings, but where n is your number of choices, and where k is the number of times you repeat the choice. Okay, so I'm going to say number of trials or repeats. All right. So now let's answer the second question. It says, if you guess on each question, what is the probability of answering all 4 questions correctly? Okay, remember probability is figured by taking the number of successful over the total. Okay, so considered success here, we're trying to find the probability that all 4 are correct. Okay, if we have 16 different ways to answer the test, okay, there's only going to be exactly 1 that is all right. Okay, because when you're filling out an answer key or you're making an answer key, okay, there's only 1 correct set of answers. Okay, so there's 1 that's considered successful over the total number of ways, which we just decided was 16. So our probability here is 1 over 16. Okay, so probability of all correct is 1 over 16. Okay, the next one's very similar. It says there are 2 multiple choice parts to the mathematics section of the PSAT. One has 25 multiple choice questions with 5 options each, and the other has 15 multiple choice questions with 4 options each. How many ways are there to answer the multiple choice parts of the PSAT mathematics section? Okay, so we've got 2 different parts here. We're going to look at them separately. Okay, so part 1 and part 2 here. So for part 1, we have 25 multiple choice questions with 5 options each. Okay, according to our strings with replacement theorem over here, okay, we're going to have n to the k possible strings or possible ways to answer this test. Okay, so we have to just put the number of choices to the power of how many times we repeat it. Okay, so part 1, there are 25 questions with 5 options. Okay, so our options or our choices is our n, our 5, and we're repeating it 25 times. Okay, very similarly on part 2, okay, we've got 15 multiple choice questions, this time with 4 options each. So our choices was 4 and to the power of 15. Okay, so we've got the total number of strings for each part separately, okay, but we're not taking the parts separately. We want to take the first part of the test and the second part of the test, okay, and tells us to multiply. Okay, so we're going to go ahead and type this all in because we know we got a really large number here. So 5 to the 25th times 4 to the 15th. Okay, recall that E is just a fancy way for your calculator to use scientific notation. Okay, so we want to write it more properly and say that that is our 3.2 times 10 to the 26, not E26. Okay, and again, we have to put a label on this. It says how many ways, so we'll say ways on the end. Okay, a really, really, really large number. Okay, so if we were talking about the probability of guessing on every single one of these questions, and the probability of us getting it correct, it would be 1 out of this very, very large number. Okay, so that's why when taking multiple choice tests, it's not the greatest idea to guess on every single one. Okay, if we narrow it down, at least we can cut these selections down to from 5 to 2 or 3. Okay, increase our odds there. All right, the next problem, we've got a few different questions all dealing with this bag of marbles. Okay, inside the bag we've got 6 blue marbles, 8 red marbles, and 6 green marbles. Okay, so that makes a total of 20 marbles in our bag. Okay, so we want to know if Jeff draws out 3 marbles, one at a time, okay, replacing the marble after each draw, what is the probability that they are all green? Okay, so we've got 3 different selections here. Okay, we're going to draw one, and then draw another, and then draw another. Okay, this is an and situation. Okay, what we've been working with so far is talking about numbers. Okay, we said the number of A times the number of B gave you the total number of ways. Okay, what we're going to talk about now is probability. Okay, it also applies with just individual probabilities of an event so long as we are working with an and situation here. Okay, so we want to draw out 3 marbles, and we want to know the probability they are all green. Okay, so we want the first one to be green. Okay, successful is considered green here, so there's 6 that are considered a success over the total number 20. Okay, so our first marble, that's the probability of drawing a green. Okay, and then we're going to put the marble back. Okay, so there's still 20 marbles. There's still 6, 8, and 6. And then we're going to draw another one. Well, the probability of getting green is once again 6 over 20. And you guessed it, the last one, 6 over 20 again. Okay, this is an example of where we can use the n to the k idea. Okay, but instead of numbers of choices, we're talking really about our probability of our choice. Okay, since all of them were the same probability and we were replacing them each time. Okay, so another way to look at this is 6 over 20 to the third power, or if we reduce, 3 over 10 to the third power, which gives you 27 over 1,000. Okay? If you want to, you can type this in exactly like you see it. Okay, go ahead and reduce it as a fraction, or your calculator will give you it as a decimal, and that's okay too. Probabilities you can write as decimals, percents, or reduced fractions. All are fine. Okay, I generally like fractions because they're straightforward, and some of the decimals we're going to be working with today may not look rational even though they came from fractions. Okay, so be careful on that. Okay, so for right now we're just going to say probability of all green was 27 thousandths here. Okay, on part B, if he replaces the marble after each draw, what's the probability that he draws 2 red marbles, then a blue marble? Okay, so his first draw is a red marble. We're going to go up here and look that there are 8 red marbles, so 8 over 20. Okay, we're still replacing the marble, so we've got 20 marbles when we put it back in. Okay, and the second one is red as well, so 8 over 20 once again. Last one is a blue marble, so we've got 6 out of 20 here. Okay, go ahead and multiply all those together. Again, you can just type it all in if you want. Okay, we can do it as a decimal or as a reduced fraction here. If we reduce, we got 6 over 125. Okay, and your calculator will give you that as 48 thousandths. Okay, so the probability of red, red, blue is 0.048, or 6 over 125. Okay, either option is acceptable. Okay, so let's talk about part C. It says, how would part A change if Jeff did not replace the marble after each draw? Okay, so the first draw is not going to be affected here. We're still looking for 3 green, and the probability of the first marble being green is still 6 out of 20. Okay, but for the next one, some things have happened. Okay, we've taken out a marble, okay, and we did not replace it. So we no longer have 20 marbles in the bag, we only have 19. Okay, and that marble that we drew out the first time happened to be green. Okay, so now instead of having 6 green marbles, we only have 5 left. So the probability of a green on the second draw is 5 out of 19. Well, on the third draw, again, now 2 marbles are out of the bag, so we only have 18, and 2 of the green ones are gone, so we're only left with 4. Okay, so multiply those all together, and we've got 1 over 57. Okay, I'm going to have you take a look at this here. 6 out of 20 times 5 out of 19 times 4 over 18. Looking at this right here, okay, it's hard for me to determine that this is actually a rational number. Okay, this is what I was saying about how decimals aren't always the greatest, okay, because this looks like it would be irrational. But hit math, enter, enter, and you can see that it actually is a fraction. Okay, so this time we've got the probability of green, green, green being 1 over 57. Alright, I want you to pause the video and see if you can figure out how part D would be done. Alright, 4 marbles without replacement, very similar to before. The first one is red, so that is 8 out of 20. Okay, the next one then we don't have 20 anymore, so it's automatically 19, automatically 18 after that, automatically 17. We just have to decide the top numbers. Okay, the second one was blue. We have not taken out a blue yet, so there's still 6. The next one was green. We have not taken out a green, so there's 6. But that last one has to be green as well, and now 1 is removed, so that changes to 5. Okay, multiply those all together, and you should get a reduced fraction of 4 over 323. So the probability of getting red, blue, green, green is 4 over 323. Alright, on number 6, we're talking about a deck of cards. We want to find the probability that if you draw 2 cards from a deck without replacing the first before drawing the second. Okay, so we're going to draw 1 card and then draw another without putting that first one back. We want to know what's the probability that they will both be hearts. Okay, first draw, we just have to figure out what is the probability of drawing a heart. Okay, you can come at this 2 different ways. You can think about, well, how many hearts are in a deck? Okay, we know we have 4 suits. We've got hearts, spades, club, and diamonds. Okay, and 52 total cards, which means there's 13 of each of those 4 suits. Okay, so the probability of heart would be 13 out of 52. Okay, well, another way of thinking of that is as the reduced fraction. We've only got 1 suit that is successful heart out of 4 total suits. Okay, so those are equivalent there. You'll notice they reduce to the same thing. All right, now we want to do the second card without replacing. Okay, so we've got 1 less card. Now there's 51 cards left in the deck, and we want to draw another heart. Okay, so we've taken out 1 of the hearts. There are only 12 left, so I have to take 13 over 52 times 12 over 51 there. Okay, so for this one, we got 1 over 17. So the probability of 2 hearts without replacement is 1 over 17. Okay, well, the second part asks us, what is the probability if you do replace the first card? Okay, well, the first card isn't affected, so I'm going to use this 1/4 because that's the same as 13 over 52. Great. Well, now I'm going to put that heart back in the bag. So if I go up here, I still have all 13. I still have 52 to choose from. Okay, and I'm going to choose again. Probability of hearts does not change if you put it back, so it's 1 over 4 again. Or think about it as 13 over 52 times 13 over 52. Okay, either of these are okay. So I've got 1/4 times 1/4, 1 over 16. Okay, so the probability of 2 hearts with replacement is 1 over 16. Okay, you'll notice that it's more likely to get 2 hearts in a row if you put the hearts back. Okay, that should make sense to you because if you put the heart back after drawing it, there's more hearts in the deck for you to choose from and to be successful with. Okay, so that's the basics of the multiplication counting principle. Next, we're going to talk about independent events. Okay, in order for events to be independent, okay, the outcomes should not affect each other. Okay, so let's read this definition here. It says events in which one outcome does not affect the results of the other outcomes are considered independent events. Okay, any selection with replacement, so those ones on the front page when we did with replacement, are considered to be independent because the later selection does not remember what happened in earlier selections. Okay, so let's flash back to our 2 hearts that we pulled out here. Okay, those were independent events, the first draw and the second draw. Okay, because the second draw didn't care that you got a heart the first time. It doesn't matter. Okay, it was independent. The probability was still 1 out of 4 every single time because you were leaving those cards put back in the deck. Okay. Now, if it's not independent, then of course the events are considered dependent. Now, it's not always easy to determine whether events are dependent or independent just by looking at them or thinking about them. For that reason, we have a mathematical definition. Okay, so events A and B are considered independent if and only if the probability of A intersect B is equal to the probability of A times the probability of B. Okay, so what we have to do here is find the probability of each of the separate events, then find the probability of their intersection, or where they both happen, and see if those match up. Okay, if they match up, they're independent and they do not relate to one another. Okay, one does not affect the other. However, if they do not match up, there's some sort of tie between your two events. Okay, so let's take a look at number 7 here. We've got a spinner with 6 different pieces. They're all congruent, so they're all the same size, meaning they're all equally likely to appear. Okay, we're also going to make the assumption that this spinner hand is not going to land on one of the divider marks. It has to land exactly on one of the numbers. Okay, that's going to make our probability a little bit more basic here. Okay, so just looking at this one spinner, we've got 6 different outcomes. 1, 2, 3, 4, 5, or 6. Okay, so the probability of choosing any of those, or spinning and landing on any one of those, is 1 out of 6. Okay, but we're not going to spin it just once. Okay, it says consider spinning it twice. Define these two events. Event A is the first spin stops on an even number. Event B is the second spin stops on a multiple of 3. So we're going to look at each of those. Okay, we'll find first just the probability of each of the events. Okay, so the probability of the first event happening, the first spin stops on an even number. Well, if you spin it, the probability of even is 3 out of 6, or 1/2. Okay, event B, we want to look at what's the probability the second spin stops on a multiple of 3. Okay, so we're spinning it again, multiples of 3. We've got 2 successful here, so 2 out of 6, or 1/3. The only thing left is to look at their intersection. What I want to know is what or how many numbers, what is the probability of the first spin stopping on an even number and the second stop spinning on a multiple of 3 at the same time. Okay, so what we're going to do for this is kind of just list out our outcomes that are considered successful. Okay, so I'm going to start out with kind of making a stem and leaf type plot here. Okay, so my first event was stopping on an even number. So I'm just going to list all of my even numbers. We've got 2, we've got 4, we've got 6. Okay, well, each of these 2, the 4, and the 6, we're going to pair up with the second event. Okay, and this second one here, it says the second spin stops on a multiple of 3. Okay, so multiples of 3 are 3 and 6. So I could have 2 then a 3, or a 2 then a 6, and that would be considered successful. Very similar, a 4 and a 3, or a 4 and a 6. A 6 and a 3, or a 6 and a 6. Okay, so this stem leaf plot that I've got going on here really represents the spin 2, 3, 2, 6, 4, 3, 4, 6, 6, 3, 6, 6. So there's 1, 2, 3, 4, 5, 6 events that are considered successful. We just have to talk about the total. When you spin twice, you've got 6 outcomes repeated twice, so 6 squared has a total of 36 outcomes when you're spinning it twice. So 6 out of 36 reduces to 1/6. Now let's go compare. Okay, if these are independent events, the product should be equal to that intersection. Okay, so I'm going to set it up, the product of the probability of A and the probability of B, and we want to know how does that compare to the intersection of A and B. Okay, so this was 1/2 times 1/3. I want to know, is that going to be the same as 1/6? So we go across here, 1 times 1, 2 times 3, and these are equal. Well, according to our definition up here, that means A and B are independent. Okay, so we'll say therefore events A and B are independent. Kind of like a little proof there. Okay, so let's take a look at the next one. We're going to do this spinner again, and we want A and B to be defined as the first spin stopping on an even number and the sum of both spins being greater than 8. Okay, so again, we want to know probability of A, probability of B, and probability of the intersection here. Look at each of these. Okay, this time we're supposed to show that they are dependent. So we know that this product cannot match up as the intersection here. So it's a little bit more difficult to come up with the intersection. You can't just assume that they're equal. In this case, they're actually not equal. Okay, so what I'd like you to do is pause the video and see if you can come up with each of those probabilities. The first one, stopping on an even number, just like before, even is half of the number, so 1 out of 2. Okay, the harder one is going to be the sum of both spins being greater than 8. Okay, so again, we're going to talk about both spins, but it has to be greater than 8. So my first spin, I can't use 1 paired with anything because I've only got 6 choices, and if I map 1 to 6, that doesn't give me a sum greater than 8. Okay, well in fact, 2 doesn't work either because that's not greater than 8. It's exactly 8. Okay, so I can only start at 3, 4, 5, 6. And I'm going to pair those with all of the numbers I can possibly get. Okay, so 3 and 6 is greater than 8. 3 and 5 4 and 5, and 4 and 6, I'm adding in my head here. Those are each greater than 8. 5 and 4, 5 and 5, 5 and 6, all of those are greater than 8. And lastly, we've got 6 and 3, 6 and 4, 6 and 5, 6 and 6. All of those are different or greater than 8. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total successes out of 36, which reduces to 5 over 18. Okay? Now, it's helpful to have these listed out because it's going to help me with the intersection here. I want to know which of these are also situations where the first spin stopped on an even number. Okay, well the first spin is listed in my stem here. Okay, so even number here and even numbers here. So I've got 1, 2, 3, 4, 5, 6 out of 36 for the intersection. Okay, we're supposed to show that this product is not equal. Okay, so let's set it up. Probability of A times the probability of B, and compare it to the intersection. So 1/2 times 5/18 compared to 1/6. Over here I've got 5 over 36, and that's definitely not equal to 1/6. So just like we wanted, if they're not equal, then they're not independent. So A and B must be dependent. The next one, we've got a fair coin tossed 4 times. We want to know the probability of getting all heads, probability of all tails, and the probability of the intersection in order to decide if these are independent or dependent events here. Okay, so probability of A is getting all heads. Okay, so let's talk about our different outcomes here, because this is different from our spinner problems that we've been working before. Okay, so just like with our spinner, we had the number of trials, number of choices to how many times we were repeating it. Here we've got a coin that's tossed 4 times. Well, a coin has 2 choices, heads or tails, and we're repeating it or tossing it 4 times, so we should have 16 total outcomes. Okay? Of these, we want to know the probability of getting all heads. Okay, well that would look like heads, 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 heads. There's no other way to say that. There's only one way, so it looks like 1 out of 16. Very similarly, getting all tails, there's only one way to do that. Tails, 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 tails. So we've got 1 out of 16 again. So now we just have to look at the intersection. Okay, so what is the intersection of getting all heads and getting all tails? Well, getting all heads, we said, was heads, 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 heads. There's only one outcome. Only one outcome again. And guess what, folks? Those don't overlap. Okay, so the intersection doesn't exist. The probability then is 0. Now, I hope that's enough to tell you that these have to be dependent, okay, because when we look at the product, we've got a number, 1 over 16, times another, 1 over 16. And there's no way that can be 0, because neither of those was 0 itself. So, A and B are dependent events. Alright, I want you to pause the video and on number 10. Alright, for the event C, the sum is 7. I've listed all the ways the sum can be 7. So there's 6 out of 36, or 1/6. For part D here, it says the first die shows a number 5. Anytime it only talks about one of the die and not 2, or one of the spinners and not 2, all you have to do is look at the probability for that one roll or for that one spin, okay, because it doesn't know what's happening on the other one. Okay, this is like a with replacement type problem. Okay, so here it's just 1 out of 6, 5 out of 6 total options, or that's 1 successful. Okay, the intersection is of course this 1 right here. It was a 5 on the first die and then a 2 with it to get the sum. So it's 1 out of 36 total options when you've got 2 die rolled. So then looking at the product, they're equal, so C and D are independent here. Okay. The last thing we're going to talk about are complementary events, okay, which you should have worked with a little bit last time. Okay, remember, complements are essentially an event and everything but that event. Okay, they have to add up to 100%, and they have to be mutually exclusive, so they have to be a situation that would not overlap. Okay, so we're going to talk about this in symbols so that we can write complements of given events. Okay, so if we're talking about equal, the complement of that would be everything but equal, so not equal. The complement of greater than is everything not greater than, so that would be less than or equal to. Similarly, the complement of less than will be greater than or equal to. Complement of greater than or equal will just be less than, then greater than. Now, the complement of and will be or. Okay, so using this information, we're going to write the complement of this event given below here. It says, let A be the event consisting of all ordered pairs x comma y, where x is greater than 0 and y equals 1. We want to describe the event, which is the complement of A. Okay, you'll remember from last time the notation, complement is just written with a bar above the letter there. So that's the complement of A. And I'm just going to write equals, so is. We're going to start out with all ordered pairs just like they did. So all ordered pairs x, y. And then we just have to switch up according to our symbols and our words that were given here. Okay, it says where x is greater than 0. So we want the complement of that. That would be x is less than or equal to 0. Then it says and, we want the complement of that, so or, and the complement of y equals 0, or equals 1, excuse me. So y is not equal to 1. Okay, so look for your symbols, look for your words, and switch everything. Okay? The rest of this worksheet is some mixed review from what we did last time and then what we did today with multiplication counting principle and independent events. Okay, so I'd like you to work through those and come ask me if you have any questions on them.